have a metathesis reaction that we've talked about. We have a metathesis reaction here that we've talked about a little bit already. It follows a general trend, A, B, C, D, A, D, and C, B. A, B, and C, D are ionic compounds, aqueous ionic compounds. Sometimes those aqueous ionic compounds can be, or sometimes A, B, C, D can be represented by a weak acid, or an acid and base reaction, for example. But in general, what's going to happen is the cations and anions are going to change places, right, and find different products. So when this occurs, oftentimes one of the products is insoluble. So here are some compounds that I want you to check and determine whether they're soluble or not using these solubility rules. Okay, so solubility rules tell us whether or not compounds are soluble simply by reading through these rules. So take a look at those, everybody. Push pause and predict whether or not these are going to be soluble based on these solubility rules. Fred, what do you think? Is the first one going to be soluble?
Yeah, that's an acetate, right?
That's right. That's an acetate salt.
Acetate salts are always soluble.
Very good. Rule 2 says that. How about this one here? Is this one soluble, Fred?
That one's not going to be. Carbonates are generally insoluble, and iron is not an exception.
Very good. How about this one here? Is silver chloride going to be soluble?
Chlorides are generally soluble. That's rule number 5, is it?
I think it's rule number 3.
Oh, rule number 3. But silver is an exception.
Yes, silver is an exception. So, good. We use these rules then to predict whether or not compounds are soluble or not. So, given this A, B, C, D component, can you guys predict the products and then predict whether or not the products are going to be soluble? Okay. What do you think, Fred? What are the products for this reaction?
That's going to be lead hydroxide and calcium nitrate.
Very good. Lead hydroxide, Pb, OH. Now, what is the ratio that those come together in?
Well, that red lead is a +2 from the first compound, right?
Yes, that's right. So it's a +2 charge. So am I going to need 2 hydroxides because hydroxide is a -1?
Yeah.
All right, and then what's the other product?
Calcium nitrate.
Calcium nitrate, like that?
The calcium's +2 as well, so you need 2 nitrates.
All right, 2 nitrates. Very good. Are either of those going to be insoluble?
Look at my solubility rules here. Hydroxides are generally insoluble. So the hydroxides are generally insoluble, and lead's not an exception.
Okay, so this is going to be solid here, and this one is going to be aqueous. Good, excellent. What are the products here?
Barium carbonate and sodium chloride.
Very good, barium carbonate. What's the chemical formula for barium carbonate?
So it's BaCO3.
Good. Whoops. More than one CO3 or no?
Nope, just one.
Okay, and then sodium chloride. And now it looks like to be balanced, I'm going to need 2 sodium chlorides, right?
Yeah.
All right. Fabulous. What are my resulting products here?
The sodium nitrate and mercury phosphate.
Very good. Sodium nitrate. Sodium nitrate, that's just NaNO3. Mercury phosphate. Now the mercury ion, it's a little bit tricky. There's more than one kind of mercury ion, but this is the mercury 1+ ion. It's kind of tricky. We're not going to go into the specifics there, so don't worry about that one too much. For this one here, what are my products?
Sodium nitrate and calcium chloride.
Very good. Sodium nitrate and calcium chloride. All right, good. Oh, and why do we say no reaction here?
Because neither of those are solids.
That's right, neither of these are solids. And so these are going to be broken up into ions just as they were when they were in solution, and there's no change going to be when I combine these two reactions together. All right, what about this one? Which one is the solid product?
Calcium carbonate.
Very good. That was fast. A, calcium carbonate. Excellent. How about this one here? Which is the net ionic equation for this reaction?
I don't know. Can you predict the products?
Okay, so if I predict the products here, I would say that the products are, let me get this better pen over here. Products are sodium fluoride and looks like water, right?
Okay, yeah, I see that.
All right, and now if we're going to break up these, some of these at least, into ionic, they're ions, right? Sodium hydroxide is going to break up into sodium ions and hydroxide ions. Sodium fluoride, that's another easy one.
Yeah.
Sodium ion and fluoride ion. Water, I know, doesn't break up. HF, does it dissociate?
I think so. It doesn't have any solubility rules information.
No, it's an acid though. It's an acid, right? Specifically, it's a weak acid. And so weak acids we don't write as dissociated in ionic equations. So if this is our ionic equation here, we'll see that our net ionic equation just has that missing, which would be C here for us. Okay? So take-home message from this problem is that if you have a weak acid in a reaction, it doesn't separate into ions when we write the ionic equation, and therefore if it reacts, it's not going to be lost in the net ionic equation. All right, now we're going to introduce to you a second kind of reaction. The metathesis or the metathesis reaction, A, B, C, D, that's what we just went over, right? But now we're going to talk to you about what's called oxidation reduction reaction. You can also call it a reduction oxidation reaction. You'll also hear it be called a conjunction of the word reduction and oxidation, which is simply redox reaction, a redox reaction, reduction oxidation. It's not appropriate just to call it a reduction reaction or just an oxidation, because those things don't happen independent of each other. Whenever one compound is oxidized, that means there's a neighboring compound that's been reduced. Okay, does that make sense, Fred?
Yeah, I follow that.
We've talked about this, these types of reactions already. For example, sodium chloride is formed from the combination of sodium and chlorine gas. This is a redox reaction. Sodium metal here starts off as just simply Na, which is, if you look at the number of the periodic table, you see that sodium has 11 protons. And this species here, there's two of them, but they have 11 protons and 11 electrons. How do I know that they have 11 electrons, Fred?
Just the same as the protons because there's no charge?
That's right. Has the same number of electrons as protons because there's no charge. How about this species right here, Cl2? How many protons and electrons does it have?
17 protons for each chlorine and 17 electrons for each chlorine?
That's right. Now, 17 times 2, 34 electrons altogether here in one of those, and 34 protons altogether. But the net charge per chlorine is 0. So we start off with two elements that have 0 oxidation state. And the sodium goes to sodium ions, or in other words, it loses electrons, right? And the chlorine goes to chloride ions, or in other words, each chlorine gains an electron. Okay? So, sodium, when it loses electrons, we call that an oxidation. And when chlorine gains electrons, or an electron, we call that a reduction. All right? So, we can look at a chemical reaction, a redox reaction, and identify whether a species has been oxidized or reduced by comparing the number of electrons that it's either gained or lost. We have to be become proficient at being able to recognize whether a reaction is a an oxidation, redox reaction or not. And there are some mnemonic devices that help us recognize whether a species is oxidized or whether a species is reduced. And this is called oil rig. Oil stands for oxidation is loss, and rig stands for reduction is gain. And what are they talking about, Fred? What's lost and what's gained?
The number of electrons.
That's right. There's another one called, another mnemonic device code. It says Leo says GER. Leo stands for loss of electrons, oxidation, gain of electrons, reduction. For me, what I prefer to do is think about an element. Let's think about element X. If element X gains an electron, it has a -1 charge. If it gains 2 electrons, it has a -2 charge. If element X loses an electron, it loses a charge, or loses an electron, it gains a positive charge. If it loses 2 electrons, it gains a +2 charge. Well, if you look at it like this, as I go from +2 to +1 to 0 to -1 to -2 down this direction, this is called reduction. All right, because that number, that 2 plus 1, 0, and -1, -2 is being reduced as it's gaining electrons. All right, so whatever method you used, you have to remember that gain of electrons is reduction and loss of electrons is oxidation. And we need to be able to look and compare elements on the left of a reaction and on the right and see whether or not the process was a reduction or an oxidation. Okay? So we can also identify what's called the oxidizing agent or the reducing agent by identifying which species has been oxidized or reduced. If I know, for example, here's my chemical reaction, sodium combining with, I'm just going to add a single atom of chlorine to simplify things, to form the sodium ion and the chloride ion. Which species has been oxidized in this process?
Well, the sodium lost an electron, so it was oxidized.
Very good. And the chlorine was reduced. Chlorine was reduced, but it oxidized sodium. Can you see that? Sodium lost an electron to the chlorine for sodium to end up with a positive charge and chlorine to gain an electron. Okay? So, when we identify the species which has been oxidized or reduced, we can recognize that the other species must have done that oxidizing or reducing. So chlorine was reduced, making sodium what we call the reducing agent. Sodium in this case was oxidized, but it was acting as the reducing agent. Chlorine was reduced, but it was behaving as the oxidizing agent. Okay, good. So looking at this reaction here, can you identify which species functions as the oxidizing agent?
Oxidizing agent?
Yeah.
Well, would it be the zinc?
How can you tell?
Because it was oxidized.
The oxidizing agent isn't oxidized, is it? The oxidizing agent is reduced.
Oh, yeah. So is it the platinum ion?
Good, it's the platinum ion. Because zinc here, you see, was oxidized. How did it get oxidized? It got electrons. Something took electrons away from it. And whatever species it was that took those electrons gave it up. Or oxidized that species. Okay, here you go. Whoops. Which species gets oxidized in the following reaction?
This is just asking for what species gets oxidized, right?
That's right.
So the answer is zinc.
All right, zinc is oxidized. That one was easy for you because you know how to recognize whether a chemical has been oxidized or reduced, right?
Yeah.
Good. How about this one?
Which chemical is the oxidizing agent and gets reduced? Okay. Oh, are these the same chemical?
What do you mean?
If it's the oxidizing agent and it gets reduced, that's the same compound, right?
Yeah, it's a good point. So that means they're only B or B or E?
B or E, yeah.
Okay. But it looks like hydrogen is the one that is being reduced. It's gaining electrons, right? So it must have been the oxidizing agent. Okay, very good. B is our answer there. All right, so now, well, we'll save that for next time. Good job.